Okay, so let's calculate the specific internal energy at state 1. So that's going to be equal to U of the saturated liquid plus the quality at state 1 times U of the saturated vapor minus U of the saturated liquid. And of course, this is all evaluated at a pressure P1 of 1 bar. Okay, let's see here. Let's look some of these values up. Let's see here. Okay, so 1 bar, specific internal energy of the saturated liquid, 417, and vapor, 2506 kilojoule per kilogram. So I have 417 plus 0.25, that's the quality at state 1. And then U of the saturated vapor is 2506 minus 417, and that all has units of kilojoules per kilogram. Kilojoule, not kilogram. Kilojoule per kilogram. You crank that all out, and you see an initial specific internal energy at state 1 equal to 940 kilojoules per kilogram. 940 kilojoules per kilogram. Okay, so we've got 940 kilojoules per kilogram. Okay, so we've got the, we got the specific internal energy at state 1. Check. Now we need to get the specific internal energy at state 2. Now to do that, we have to know something about state 2. We don't really know anything in particular except that it's a saturated vapor. So state 2 is on the saturation dome to the left of the critical point. So we need to know another property to place us to know the state. We need to know something else about state 2 besides the quality. I need a temperature, I need a pressure, I need a specific volume. Specific volume. We know it's an isochoric process. That means that the specific volume at state 2 is equal to the specific volume at state 1. So specific volume at state 2 is equal to specific volume at state 1. It's a rigid container, isochoric process. The mass isn't changing, so specific volume will stay the same. Let's see here, specific volume at state 1. Let's calculate it. Okay, at 1 bar, let's see, the saturated liquid is 1 times 10 to the minus 3. So 1 10 to the minus 3 cubic meters per kilogram plus 0.25. And then we have specific volume for the saturated vapor. 1.694 plus 1 times 10 to the minus 3. That's the saturated liquid. And this all has units of cubic meters per kilogram. I'm going to get a little lazy here. The 1 times 10 to the minus 3 is so small in both these terms. I'm going to neglect it, and I'm going to immediately calculate 0.25 times 1.694 cubic meters per kilogram. So 0.25 times 1.694, and I get 0.423 cubic meters per kilogram. Okay? So specific volume at state 1 is equal to specific volume at state 2, 0.423 cubic meters per kilogram. Okay? Now, oops. Sorry, I plugged in for all the specific volumes in my quality equation. There's the quality, 0.25. I neglected the specific volume for the saturated liquid, very small. And I just did 0.25 times 1.694, which is the specific volume of the saturated vapor. And I get 0.42 cubic meters per kilogram, okay? So we know this is a isochoric process. So here's V1 equals V2 equals 0.42 cubic meters per kilogram. So state two is a saturated vapor with a specific volume of 0.42 cubic meters per kilogram. 0.42 cubic meters per kilogram. Let's see if we can crank that out. So U2 is equal to U at a quantity of 1 and a specific volume of 0.423 cubic meters per kilogram, okay? So how are we going to calculate this? How are we going to calculate the specific volume of a saturated vapor? So this is U sat vapor evaluated for a specific volume of 0.423 cubic meters per kilogram. That's what we're looking for. All right? Well, let's go back here. So let's see if we can find for a saturated vapor. Let's see if we can find for the saturated vapor a specific volume of about 0.42. Might have to do a little interpolation here. Vapor 0.4, I see a 0.46 and I see a 0.37. So you're going to need to interpolate between these 2 points. Looks like it's going to be about approximately halfway between. Okay? So through a little interpolation, I find the specific volume at state 2 is equal to 2,557 kilojoules per kilogram. If you look here, 2,557 is approximately halfway between these 2 data points, okay? So, from interpolation, I get 2,557 kilojoules per kilogram. Interpolation. Okay, I interpolated between a couple of data points on the table. 2,557. Okay, so now we have U2. We've got everything. Let's plug in. Let's see here. We have 5 kilograms of the stuff. 5 kilograms. U2, 2,557. U1, 940. And this has units of kilojoules per kilogram. The current was 8 amps and the voltage was 110. So 8 amps times 110 volts. And amps times a volt gives you a joule per second. So notice the kilograms cancel out here. And this thing has units, so the voltage times, I guess I'll write it down one more and then I'll group all the units together. How about we do that? Got to be a little careful with this voltage times current. Let's see here. So we have 255.7 minus 940 times 5 divided by 8 divided by 110. And I get 9.18, and then my units are kilojoules, and then I have an amp times a volt. Okay, now the amp times a volt, as I said, had units of joule per second, or if you like, a watt, a joule per second. I need to convert that into kilojoules so that it will cancel out properly with what's in the numerator. Let's see here. So there are 1,000 joules per kilojoule. Okay, the kilojoules, kilojoules cancel out and I get joules. The joules cancel out and I get 1 over seconds. So I get 9.18, 10 to the 3. Joules cancel and I get 1 over seconds and I get seconds. So delta T is equal to 9.18 times 10 to the 3 seconds. If we want to rewrite that in terms of minutes, so there is 60 seconds per minute. The seconds cancel out. So 9.18 times 10 to the 3 divided by 60. And that gives me 153 minutes. 153 minutes. Kind of going off the board here. So the heating time is equal to 153 minutes. That's it. Heating time is 153 minutes. Okay, so this is kind of an interesting problem in the sense that we had a two-phase mixture to deal with, not an ideal gas. So that complicated things a little bit. We had a quality to worry about and using the saturation tables. We also had time in this problem. So I used the rate-based energy equation and then integrated it over the process to extract out a delta T, which is what I'm looking for. And by the way, I think I was calling this delta T from 1 to 2. Delta T from 1 to 2, okay? All right.